All right, today we have our very own Nikolay speaking on the infinitesimal structure of BunG.
Right. Yeah, thank you for the introduction. So today I'm going to discuss two main ways of describing these so-called jet spaces of BunG. And I want to make it very explicit and concrete. So I hope to make this sort of like an easy, not too much theory talk. Let me first introduce some notation, which will be fixed throughout. So C will be the underlying ground field. And then G will be an algebraic group over C. And then we're going to fix a principal. Well, okay, yeah, let me first say X will be a smooth projective curve. C. And now we're going to consider a fixed G bundle over X. And we're actually going to make one additional assumption on this P. We're going to assume that it has no small symmetries. No infinitesimal symmetries, which means that there are no global sections of this sheaf of infinitesimal symmetries. I remind you this G sub P is the associated G bundle where we mod out by the adjoint G action. Okay. And also now let me introduce the main definition for today, namely the infinitesimal jets. So these will be denoted by well, okay, before that, one more thing I should mention is that M will be the coarse moduli space of BunG, which means that we only consider the underlying, we don't consider the stacky aspect of M. We only consider G bundles without automorphisms. There's no stacky feature, and this is actually a scheme. And now, to any scheme, we can associate so-called infinitesimal jet spaces, and these will be denoted by JP M. And this will be sort of, well, we consider the maximal ideal of the local ring of the sheaf of functions on M modulo the n plus 1. So M of this P is the maximal ideal. And maybe I'll just make a comment. The zeroth and the first order jet spaces are easy to describe. So the zeroth order jet space will just ideal mod ideal. So this is just a point, and we can identify the point with just P. And the first order jet space is just, well, M mod M squared is the Zariski cotangent space. So this is dp_m star. And sort of the main goal for today is describe explicitly JPN M for all M. And we're going to give sort of two seemingly independent descriptions. One coming from like a purely algebraic motivation. This is what we will lead up to discuss, like conformal blocks of Kac-Moody algebra. So that shouldn't make sense now, but it hopefully will later. And the other will be coming from deformation theory. So we're going to associate something which sort of has roots coming from the Chevalier complex of G sub P, the associated sheaf of infinitesimal symmetries. Okay, so any questions so far on the notation?
So can you just remind us of the precise definition of like the corresponding spaces?
Well, for me, it consists of sort of semi-stable bundles such that there are no automorphisms.
The automorphism is discrete.
Yeah, well, I guess I've seen like the most general ways you say the automorphism group is like the center of the group, but I assume that maybe a simple complicated. Sure. Yeah, it can be discrete or just even better, just empty, zero. All right, so let's revisit the first order jet space indeed. So tangent space revisit. So I remind you that in Professor Ginzburg's talk, we found that the tangent space of BunG is isomorphic to H1 of the sheaf of infinitesimal symmetries. And we actually proved this like in an unusual but really cool way, like the Tanaki formalism. More classically, this is proved using like a deformation theory type argument. Namely, we can construct a short exact sequence where G sub P is the submodule and the tangent sheaf is the quotient, and the extension is the so-called Atiyah algebra. And then we can exhibit a map going from H0 of the tangent sheaf in the TPM to H1 of G sub P. This is called the Kadeira-Spencer map. And then we need to check that this is, in fact, an isomorphism of vector spaces. And that's where we need to use the assumption that there are no automorphisms. And this is like a purely cosmological way of proving this isomorphism. And then maybe I can continue this like detour. One may try to develop an analog, like a higher Kadeira-Spencer map, where we can replace the tangent space with like the n-order tangent space, which is defined as like the dual of the n-order jets. And instead of mapping to H1 of GP, we replace GP by a complex of length n, and we replace H1 with the nth hypercohomology. And again, you exhibit the map from one to the other as a coboundary map. And again, we can show that it is an isomorphism basically following from this assumption. And this is the approach used by Heineck. I think he's the first to really use like this method. And then for BunG, it was proven like very carefully by Esnol and Nikolay. I can give references later. But anyway, so returning back here, I want to explain what the tangent space should be thought of algebraically. And to do this, we have to revisit the uniformization map. So recall what there exists a uniformization map which maybe I can call it U from GK mod GO to BunG. I guess I should explain what K and OR. So K will be the punctured formal disk. And O will be just the disk. And maybe I will introduce some more notation. Let's O sub out denotes the functions on the curve over the punctured curve. So here we fix a point on the curve. And then we have this O sub out is here. And maybe I'll write this now. We assume this for simplicity, x minus a point is out. In general, x is a projective curve, so if you remove finitely many points, it will be affine. And just assume we're lucky after 1 point.
That's always true though.
That's okay, yeah. Great. Okay, and yeah, let me introduce some more notation. So I guess I'll have some, since I'm writing here notation. Let G sub K be G tensor, the field of Young polynomials. G sub O be G tensor, the foreign polynomials. And G sub out be sort of the G tensor O sub out. Okay, and now going back here, this is the affine Grassmannian, and sort of the kernel of this map is G of O out, and we can rewrite this as saying that U mapping from D of O out mod D of K mod G of O is an isomorphism onto BunG. And
you assume G is symmetry.
yeah, maybe I can even assume it's simple.
So what does it mean? G O GK GO, it's actually just a set, right?
GK is, well, I think of GK like K valued entries of G, or like
Saying this is equivalent to BunG X, or BunG is a stack, right? So you know things like K points.
the K points, or the C points.
It's closer to his points.
The C points.
Yeah, the C points. Yeah, I mean, this isomorphism, really what it's saying is, given a G bundle P, we can trivialize it on the formal disk, and we can trivialize it on the punctured curve. And then the compatibility constraint is saying that the transition matrix on the intersection, which is the punctured disk, is an element of this GK. So like we have a choice of two trivializations plus how they glue.
I'm saying yes, it's equivalent to groupoids, but it's not.
You can make it in families as well.
Huh?
I think you can make it in families as well. I was just saying for sequence.
Yeah, so like all pieces. Yeah, I really wanted to avoid using like stacks in this talk. Like everything for me will be a classical logic vector. Okay, so now we can actually read off what the tangent space should be. So I can write this down sort of like hope that TP of BunG will just replace the group by the algebra. So we kind of hope that it's G sub K mod G sub O plus G sub out. Now, of course, this cannot literally be true for a few reasons. I mean, most, like obvious is, well, the left-hand side, there's a dependence on P. On the right-hand side, we don't see this. But maybe a more serious problem is, in general, if we have a quotient of two groups like G mod H, where H acts freely, then the tangent space does behave correctly. Namely, it's the quotient of the Lie algebra mod the algebra, but G of O out does not act freely on the affine Grassmannian. So taking the tangent space of like a group mod, a group which does not act freely, it's not so clear whether this holds. But I'm going to show that this actually, it's like something almost like this does hold. And for this, we're going to explore the so-called like local to global lemma.
So the proof you're going to do, it will be true only if it's like, I think this statement is true also not in a semester. Like in the level of the algebra, it should be true for any reductive group here. But here you're going to prove it only using the statement about the reductive group itself.
So what I'm going to prove is that this quotient is equal to H1 of GP always for all P. And then I'm
asking about G now.
Yeah.
Like, I'm thinking if like I think this statement is true also without the assumption that it's true in the level of groups. Like it can be true even if in the level of group it's not true. The level of the algebra it will be true. Okay, we'll see later how.
So I think this is only true like as a vector space. I don't think there's a.
No, I mean even for like reductive group, the first statement is not true if it's not semi-simple, but the second statement is supposed to still be true.
So I'm not very confident. What I am confident is that the right-hand side is equal to H1 of GP holds always, like in general, for no assumptions on the group G. But whether H1 equals TP BunG for all G, I'm not very confident about that. So I'm afraid to make such a claim. Okay, so is that okay? Okay. Here's a lemma. So I actually saw this lemma formulated this way in Justin's notes. It's a very like useful lemma which we'll see like two immediate corollaries. The statement is if you have a quasi-coherent sheaf, on a smooth projected curve X, then there is a short exact sequence of sheaves on X given by F, and then we pull back, push forward along the disk. So I'll explain this notation shortly. So we pull back, push forward on the disk, and then we pull, push on the punctured curve. And then sort of on the intersection, you pull, push along K. So here, let me explain the notation. K is the inclusion of the punctured disk to X. O is from the disk, and K out is from well, I guess I can just say X minus X.
So this should be spec K and spec O, I guess. Oh, sorry, K is spec. Okay, sorry.
Yeah.
I see.
Yeah, at some point I will transition to replacing K by D sub X with a star and O by D sub X. But for now. Okay. And the proof of this is very simple. So simple enough that I can actually maybe even write it down here. This statement is local on F, checking exactness is local, so we can assume that we're working over an affine space. So A will be some like the theorem ring, and then we can further assume that by possibly shrinking further that this little x is just the vanishing of some polynomial.
So is that x equals that?
Okay. And yeah, and then let M be the associated module of the global sections of F. So let's convert this sequence into a statement about modules. So we want to check the exactness of the sequence going to M. And now, well, if you pull push along the disk, it's I think this will be the completion of M. So the disk is CTT or C bracket T. And now if you pull push along the puncture disk, it's like you're inverting F.
It's not quite the completion, right? It's like it's the power series ring tensor, which is
Power series.
just different from the completion. Kind of like it, and it's not finally generated. These are right.
Maybe I need to type them once. Yes. Okay. So.
Yeah.
Thank you.
Yeah. Oh.
Thank you. Okay. And then like this. And we actually saw this in Tom's talk. This is checking the exactness of this is precisely the statement of the Whewell-Losslow theorem. And you can see the original paper of Whewell-Losslow, or you can read Tom's like, very nice notes on this. Okay, so let me give some corollary. Apply this. Yeah, so now, since x minus little x is affine, we can apply global sections on this. And now we have H1F, and then the H1 of this term, well, H1 of affine and H1 of affine is 0. So the sequence terminates at H1 of F. So we have one exact sequence F of O, F of out. Okay. H1 of F. And actually, this is short exact. No, it is long exact. But what I'm about to say is apply this now to the sheaf of infinitesimal symmetries, which we assume has no global sections. Then it does become short exact. And moreover, we can trivialize any bundle on the curve. So trivializing G sub P over the disk is exactly G sub O. And trivializing it over the punctured curve is exactly G out. And over the punctured disk is exactly GK. And then H1 is H1. And over here, the map is given by the check for boundary. And like you take two sections and then subtract them. Here, after choice of trivialization, one can check that the map takes two tangent vectors and it maps to C1 minus phi C2, where phi is a lift of P. A lift coming from the uniformization map. So thus we deduce that H1 of GP is equal to GK mod GO plus phi G out. And this holds without any assumptions on G. Like we can replace this by like any vector space with a G action. We don't need any assumptions on semi-simple, anything like that. So this is why I'm confident we can always write this way, and then sort of like using Kodaira-Spencer or I guess Tanaki, we can also identify this with tangent space.
But you're using here the fact that F trivializes over X minus the point, right?
Yeah, yeah.
Which is not true for a general like that. I think that does actually use the simplicity, right? Like for example, if G were a torus, like, there's no guarantee the point. Trivialize.
Yeah.
Okay. So it's
Okay.
Maybe I'm missing something, but it appears that the description of the tangent space that you formulate as a bulk, it does not depend on the particular thing. We can give the same description for any at any point of BunG.
Phi.
What is
So the dependence on P is observed here.
you know, but here you say that it's not going to depend, right? The whole.
Yeah, here I explained, but this is
It's not wrong.
not literature.
Okay.
Yeah, not.
Okay. So phi depends on P and then it's the image.
Yes. And by the way, you can, I mean, if you really try to write down what elements here look like, you will sort of see how, like, there's, I mean, you can immediately see that it's finite dimensional. Like this, I guess this is, you can choose a convenient phi where phi is a diagonal matrix. This is some, like, some theorem, Berkhoff decomposition, I believe. And once you choose phi to be diagonal, then you sort of see like G sub k, you have like arbitrary negative degrees, but then you truncate the positive degrees and then you have, yeah. So you can deduce that it's finite dimensional, which is not immediately clear. And then you can also see there's like some root system combinatorics going on, but I don't want to get too far. Okay, so there's also another.
The dimension also can drop, right? Or random space, depending on the point.
Yes.
It's not the same dimension. So
But I think because of the assumption that H0 vanishes, it actually is
constant, right?
locally constant.
Yes.
Because the Wheeler characteristic is locally constant, so H0 vanishes.
So that's only for the force.
Yeah.
For the
We
force.
assume.
Yeah.
Yeah, I actually don't know. I mean, yeah, I don't know what the dimension will be if you assume there's automorphisms. Probably you should subtract it.
In general, the Wheeler characteristic will, that's like the sort of kind of definition.
Basically the force.
H1 can come.
The force model space is basically smooth, right?
Yes. Yes, exactly. Okay. Now there's another corollary, which is actually something we're all familiar with. It's Serre-Drouin for curves. By the way, this lemma, I mean, this is like Sasha's favorite Tate linear algebra is the term used here, where you make a cover of the curve by removing a point and then adding a formal disk around this point. And then you sort of try to work with these two separately. This is called Tate linear algebra. And then here, the proof for solidity is using Tate's linear algebra. And again, I refer to Justin's notes on this, explained very nicely. Let me formulate it here and sort of just explain the two main properties. So let be locally free, sheaf over, again, smooth projective curve X. Then there's the canonical isomorphism between H1 of F and H0 of the dual sheaf F twisted by one forms. And the proof, there's really like two steps. First is you give
Well, sorry, if Justin, if you would move the camera to the forward position.
Yeah, sorry.
No worries. It's I made a lot of mistakes when I was camera operator back in the day.
It's basically, you're going to prove this by reducing to the case of the disk first, of the punctured disk. So the statement for the punctured disk is the following. There exists a perfect pairing from global sections of. Now I'm going to switch notation. And this map is the residue map. The reason why I say it's the residue map is, well, we can identify the space of F is locally free, and then say it's a rank R. And then if we evaluate it on spec of C ZZ, we have it just R copies of C. See? And here is going to be R copies with a DZ, and the map is you take, and the map is already on here. Sorry, we'll work over polynomial or polynomial. And the maps to the residue. And the reason it's perfect is clear. If you have something like z to the I, then you take the corresponding z to the minus I minus 1 dz. And then the residue is gone. Next is that you can actually descend. This induces a pairing on the following. So this a pairing on so in general, if you have a perfect pairing of two vector spaces, on one side you quotient, on the other side you take sub. So here we take a quotient. Then here we take the sub. And yeah, it's a plane that's also. And this follows from the residue theorem. So to say a few more words, what I need to do is say, suppose I take a one form defined on the punctured curve, and then I pair it with a function also defined on the punctured curve. Then they multiply and give a scalar valued one form on the punctured curve. But you also know for any projective curve, the sum of the residues is 0. Here, there's only one possible residue. It's at little x. So the residue at little x is 0. So this shows that if you restrict to this sub-vector space, the quotient here is in the kernel. So this goes in one direction, and then the reverse direction, well, we can do some more work, but it's actually, it's not too much extra. This is, like, are put strong because, like, having the property that the sum of the residues is 0 means that the form is defined globally, like this is a actual equivalence. So, okay, oh. Stop here, and then this one the proof. And now, yeah, so I want to say now a few more words of how to generalize this construction. But are there any questions?
Just one comment maybe, which is I think to prove state reality this way, you just need to allow several punctures, right? For the same kind of reason we were discussing before.
Yeah, I
But
assume F can be trivialized on just one puncture. I think.
Oh, sure, but that's a very strong assumption.
Yeah. So in general, you have to remove finite again.
Right.
I'm keeping it very simple.
Yeah.
But absolutely it's correct. Okay, so let's now go to higher ends. Okay, so the starting point is again, so we know now that the tangent space of BunG may be identified with this double quotient sets. And now this is like the dual of the first quotients. Now, to upgrade this to higher order, we need to introduce like n orders of freedom. And the natural way to do this is to replace the algebra by the enveloping algebra, but truncated up to degree n. And
Wait, Nikolay, I'm gonna say it's 4:45. Do you think we should break now, or should we just since you're starting?
so we started 5 minutes late. So
Okay,
I gave myself 5 minutes extra.
Okay, cool.
Thank you.
Just making sure you know that.
Yeah, I just want to give some definitions. Yeah, no more theory, just definitions for the end. Okay, yeah, thank you. And so this is where I will now introduce the following notation. So let's this boldface M be the enveloping algebra maybe. So it's like the enveloping algebra of GK modulo the ideal inside generated by GO. And then boldface M sub out will be a quotient of this. So this is a GK module, G sub K. And we know that G sub out embeds into G sub K. We sort of used this many times, but yeah, this is like the Taylor expansion around the point X. And so we can consider the co-invariants. So we mod out by the left G out action. And these two spaces have names. So this M is called a vacuum representation. for the affine Kac-Moody algebra. Fine. And this space is, it's actually called the space of coinvariance. And like the Kac-Moody algebra is G sub k for us. And now the dual of the coinvariance also has a name. It's called the space of conformal blocks. Or again, affine Kac-Moody algebras. So these are like very commonly studied objects in the theory of vertex algebras. These are like these arise in vertex algebras. And without really saying like precisely what all this means, I'll explain at least why they arise. It's the following theorem. So the theorem is that there's a perfect term on the nth order jet space of BunG with the conformal blocks truncated by n. So here where PBW filtration on UChicago induces a filtration. Anytime we take a quotient of something with filtration, we get induced filtration. And this is like taking two quotients. Filtration on. And
so this space of covariance is, are we using B here to define in out? Like it's.
Yeah, that's a very good question.
Like
I think
B of G out.
technically I should put phi of G.
Yeah. It does depend on P, right?
Yeah. So basically, yeah, exactly. Thank you.
That's also for time.
Yep, absolutely. Thank you.
What was this?
The linear dual. Just the vector space. It is actually finite dimensional. No, M alpha is not finite dimensional, but the M is. Yeah. And this theorem is not difficult to prove, actually. I'll write down in proof in quotation marks. This is the classical, it boils down to a classical statement that degree n polynomials pair perfectly with order and differential operators. So why do I say that this statement boils down to that? So the nth order jet spaces, loosely speaking, it's you consider a Taylor expansion and then you truncate at degree n. And then M out, it's built out of the Lie algebra GK. And the Lie algebra GK itself is like differential operators on the group GK. So that's what's going on. If you want to be a little more precise, you can. Yes. And just the degree one is like the order one differential operators.
Invariant differential operators.
Yeah.
Yeah.
And then to be more precise, you can, again, this nth order jet space on BunG, it's like using uniformization. So if you express BunG as a double quotient GK mod GO mod G out, functions on a double quotient, again, you can think of them quotations as functions on GK, which are left G out invariant and right G O invariant. Now, what is this? Well, it's basically the same thing. It's differential operators on GK, modulo differential operators on GO, modulo differential operators on G out. So I mean, this is maybe hopefully convincing that you can at least expect this to have a perfect pairing. And yeah, the proof of this is not too bad. And maybe I want to mention one theorem before the break, which we will not prove, but we'll see in talk 7. So Nick will prove this. So theorem. And this is called the Borel-Weil theorem for conformal blocks. And the theorem, I mean, it's very easy to write down. It's saying that if we consider a line bundle on BunG, or maybe it was saying this, there exists a line bundle on BunG whose global sections is exactly the space of covariance. And we'll prove the other Nick, not me. So there's a classical way to prove this. Again, I think even BunG will also discuss this. But then there's a very modern proof, like from Nick's PhD thesis, and then turned into a paper just like 2 years ago, which gives like a very geometrical argument for this. And the reason why I say it's Borel-Weil is the analogous statement for just the algebras is global sections of G mod B. You can consider like a line bundle on G mod B whose global sections gives you like your simple representation of the algebra. And this is like what so I guess I wrote down BunG, which is like a double quotient. There's also a statement that global sections of the Riemann some line bundle is replace and out like M. So that's also something true.
And there is some line bundle such that
Yes.
yes, there is
Yeah, there's some line bundle whose global sections are M out, and there's also some line bundle on Riemann whose global sections are M. All right, so yeah, let's take a break here. All right. So I should have mentioned this at the start, but let me just say it again. So the main references are these 3 papers. Ginzburg paper on resolution of the diagonal is actually a generalization of the original paper by Beilinson-Ginzburg called Infinitesimal Neighborhood of the Moduli Space of Principal G bundles on a curve, like before they introduced BunG terminology. And in both these papers, there are no proofs written down. So I'm going to sketch a proof here. And then Beilinson-Drinfeld polyvector fields for FM Kac-Moody algebras is what I'm about to discuss right now. So those are the main methods. Okay. So yeah, in the first half, we sort of gave one description of the jet spaces. It's like this space of conformal blocks, which are the dual of this space of covariance. And now I'll give a sort of totally different perspective. Coming.
Kac-Moody algebras and differentials.
Yes, exactly.
Fully differential.
Okay. So yeah, now comes the sort of deformation theory motivated approach. We need to introduce some main definitions again. So consider the space of top degree forms on x to the I. So x is still a smooth projective curve. which are regular outside of delta. So I haven't defined what delta is. For now, you can just think of it as any like closed subset of x to the I. You can do a variety. But the sort of differential forms are regular on the complement, and then on the complement, they have simple poles. Sorry, on delta with simple poles on delta. And maybe some other standard notation for this is actually to write down log delta. The reason for writing log delta is because like a prototypical example of this is dx over x. So this is a differential form defined on P1, which is regular everywhere except that x equals 0. And then x equals 0, it has a pole of order 1. And of course, dx over x is equal to d log x. So that's why there's this log. And then in general, the forms are like d log f, which is df over f. Okay, and there's sort of one main property about such forms is that if delta is a normal crossing divisor, so it's given by like it's cut out by some polynomial, and then like this decreases the dimension by 1. Then there exists a short exact sequence from forms with simple poles on delta. Then we take the residue at delta to then get forms on delta, which are regular everywhere. So if we tilt to only that points, and then the kernel, well, surely every form which is regular on x to the I minus 1 will have residue 0. So we have this short exact sequence, and yeah, I will not use it, but I'm just writing it down so that you can get like an idea of what this is. So it's like you extend like two regular differential forms. And
Wait, sorry, how do differential forms on x to the I minus 1 not to differential forms on x to the I?
yeah, maybe it's x to the I.
Maybe it's just x to the I.
Yeah, in my notes I put to the I minus 1, and as I was writing, I realized that it's probably incorrect. So thank you. Yeah, so if a form is defined everywhere, then it has no poles on delta, so it's residue. Okay, that's kind of. Yeah, and then also let me now give another definition. So we define the Lie bracket map. Locally, it's given by just taking the commutator of the last two vector fields. Okay, and now comes the scary part. So it's define this sheaf omega sub n. So I'll say sheaf in quotation marks. So given an open set U inside X, I consider the collection of n plus 1 tuple of forms defined over U to the I. So omega I is a section over u to the I. And it's an I form with values in GP star tensor I. And it has logarithmic poles along the diagonal. And I'll make a few comments. So I take such forms so right now I just have like a direct on vector spaces, but they need to have some compatibility constraint. And the compatibility is that if I take omega n, then take its residue along the diagonal delta n minus 1 comma n, then I should get the previous one, but coming from this. So let me write this. Residue delta I minus 1 of omega I equals this I star of omega I minus. And so where delta in this case here is like the big diagonal. And delta I minus 1 is xi equals xi minus 1. And here, p sub I star is, I take the linear dual of this one. Okay, so let me spend a couple of times just motivating why we consider such a guide. So what this is saying is we have log forms on the diagonal whose residues are built up of some co-bracket expression. That's what this map is saying. So if we have two forms defined away from the diagonal, then they commute. But if we have forms on the diagonal, then the residue is just given by a co-bracket expression. And
sorry, you're saying delta. Oh, I see. Sorry, I missed it.
yeah, and yeah, I ran out of space, but maybe I can say log. Yes. Okay, so where does this come from? It actually comes from the Chevrolet complex. Yeah, so the claim is that if I take omega n of x, this is exactly the nth jet space. And so let me just get a detour. There's a general philosophy in deformation theory that says like the local geometry of a moduli space, rather, in other words, like the deformation theory is governed by the Lie algebra cohomology of a certain DGLA. And to compute this Lie algebra cohomology, you need to take a Chevrolet complex and then take its cohomology. So let me explain what this means. Is if I have G is a differential graded the algebra, we can associate this Chevrolet complex C G, which is given by taking the dual of G, shifting it by 1, and then taking the symmetric algebra. So like the ith degree cochains are given by the ith degree, at most ith degree symmetric algebra. And
Shifted by -1.
Yeah, I always
Technological or technological minus.
Well, it doesn't matter, right? It's placing in cohomological degree 1. So it's shifted by -1.
okay. Yeah, I never get it's fine, correct. Okay, so in our case, so G will be I mean, I'm going to write something which is not literally correct, but it should be sort of like a sense of what's going on. We take R gamma of GP. So GP, again, just a reminder, it has no global sections. It has an H1, this is the dependent space, and then it's also true that it has no other higher H's. So it's like it's concentrated in degree 1. And then what we do is we take like the dual given by star duality. So then we have GP star tensor dualized to sheaf. This is the dual of GP, like in a direct setting. And then you take the symmetric algebra of this is equivalent to taking the ith tensor power and then taking SI invariance. So now I told myself I will fix this, but then I forgot to fix this. I want to write SI invariance here. Very important. Okay, so if I take the Chevrolet complex to this G, I get this. And this does not actually work. What I need to do is twist it by log delta. So I'll take forms which have and so this will be sort of like the I coach. So that's when you look at the what I've written down here, it's the exact same thing. So here, yeah, you need to take box times. This space is really motivated by taking Chevrolet complex. Okay.
So there's no R gamma in the second line. Seems like the first line you're saying choose something global, and then you're considering the GP in the second line.
Yeah, so yeah. So this is just a detour motivation. I'm not making rigorous statements. I'm just trying to motivate why we consider space.
The ship disappears because of the side duality.
I'm sorry?
The ship.
Yes, the shift is accounted for by side duality. Like GP is concentrated in H1, then we take side dual, it becomes GP star, tensor dualization. Okay, anyways, yeah, this is like a before. Now, let me make one more comment so we can similarly define. So here I define it on an open set of X, but I can also define it on the disk and on the puncture disk. And also define omega n dx and omega n dx times. So here is the disk, and here is the puncture disk. So it's said earlier, I'm going to change from using K and O and using D sub X and D sub X star because I'm using, like here is spec of the completion of X along little x, which can be identified with C bracket T. But I'm not doing it here. And then just to give sort of like a idea of what this will look like, I mean, we just mimic this idea. So namely, we will say omega 0, omega n is inside. So I'll explain what forms are here. If omega I is inside G tensor C is 1. Fine. Is 1. Fine. Such that the residue of I'm going to run out of space here. such that omega I has poles only on z j equals 0 and simple poles on the diagonals. And on the diagonals, there's a special residue. The residue, for instance, along z I equals z I minus 1 of omega I is equal to a I star of omega minus 1. And I claim, yeah, so where is this coming from? This space here, it's exactly taking this equals the trivialization. Yeah, so there's a star here. The trivialization of GP restricted to this disk. And multi-copy of the disk, where I define it as like spec of the word field of different polynomials and I variables. So yeah, I guess like, I'm using that GP restricted to disk is equal to GP. This implies that. Okay, so there's a global picture. So let's take the main theorem now. So-called universal picture. So I can consider jets on the group GK. And I can consider these differential forms on the punctured disk. The claim is that there's a map, and in fact, this map is an isomorphism. And then I can also consider jets on the affine Grassmannian. So this will now be and then this isomorphic to these log differential forms on the disk. So sort of just to remind you, here I allow poles only on the diagonal. Here I allow poles on the diagonal and the zi equals 0. So certainly, if I allow more poles, there's a injection. And again, this is like what I denoted as a stuff. And then I can also consider jets on BunG. And this is isomorphic to the global differential forms with logarithmic forms. So in Beilinson-Ginzburg and in Ginzburg, so the two references up there, they formulate this isomorphism. In Beilinson-Drinfeld, they formulate 1 and 2. And we will sketch the proof for 1 and 2. This is a good picture. And by the way, another reference for this is in Benz v. Frankel's book on vertex algebras. They give the exact same universal picture, not for the Kac-Moody algebra, but for the Heisenberg algebras. Like there's such a description of jet spaces in various analogs, like various moduli space problems. Like the Heisenberg case describes like the space of curves. Okay.
Sorry about it. It's kind of strange. The differential forms is a complex. Right?
A vector space.
They just
These are
it
just
has on this function. This is has 2 0 degrees, right? There's 0 forms and 1 forms. So there's a gradient. What is the gradient response on the left hand side?
It's always one forms, right? It's their top.
Oh, you mean it's omega means only 1 forms.
oh, omega always means top forms.
Oh, okay, sorry.
Yeah, sorry. So here it's only so omega n is like a collection of n plus 1 two-fold forms, where each omega I is a top form. Each omega I is an I form. It's an I form on x to the I, which is regular away from the diagonal, and on the diagonal has log poles, simple poles.
So these things look like you have a bunch of top forms on the disks.
Yeah. Yeah, I mean, I guess I can write that multiple. So locally, omega I is the one. Z I is Z I of omega n minus 1 over Z I minus Z I minus 1 plus something regular. Like regular in this expansion, and this phi sub I is a co-bracket expression. And so then if I just keep unwinding more and more and more, what I'm saying is just like at the very end, I'm going to have some expression built up of just commutables. Like the residues really only consist of symbols involving commutables, and this is, I mean, it's like the answer is like it's a Lie operator. So is such a structure. Okay. So I want to like give a sketch of the proof for 1 because it's essentially 2 and 3 will have the same proof. So isomorphism 1 holds, and so I'll break it down to like 3 steps. So step 1 is we construct a residue parent. From GK tensor n times times omega n dx. And what this, maybe I'll say m for all m. What we do is we take m vectors in GK paired with the n plus 1 tuple. So what we do is we take the nth form and then omega n has like GK star tensor m. So we pair GK with GK star, we get something scalar value. We do this m times. So this defines me a scalar valued differential form on x to the m. Then I take the residue like m times. So I take first the residue at Zn equals 0. Then at the very end, I take residue at Z1 equals 0. And I mean, this is a well-defined pairing.
Wait, what does triangular brackets mean again?
It's the perfect pairing on GK with GK star.
Okay, you're pairing it with the differential formula.
Yeah, so first I pair the functions. So like first I kill the GK and the GK star, and I get something scalar valued. So I have a scalar valued form on C parentheses Z1 Zn. So this omega n has like a dz1 dzm term with its coefficient being just some regular functions, some Laurent polynomial in answer.
The G stars are only part, or sorry, the omegas are G star values.
Okay, G star value.
Ah, okay, so maybe I want to say this. So I want to pair G with G star.
If you look at the definition on the top right, right?
Yeah, so the omega i's are sitting inside here. Thank you. So I pair the G and the G star, get something in C, and then then I have some like function here, and I take the residues along all the zi's equals. Okay, so I define it on like a tensor algebra, and the claim is that this actually descends to the enveloping algebra, and this follows from the so-called Partian residue formula. So claim descends to a pairing from UGK times omega n. And this follows from and Partian residue formula is just a two-dimensional analog of the residue theorem. So written out explicitly, if omega is a two-form on x2 with poles only on z1 equals 0, z2 equals 0, and z1 equals z2, then we have the following identity: residue z1 equals 0, residue z2 equals 0, omega minus residue z2 equals 0, residue z1 equals 0, omega equals residue z1 equals 0, residue z1 equals z2. Okay, and then maybe it's hopefully I can convince you this corresponds to taking the to show that the form descends, essentially you need to show that psi1 psi2 minus psi2 psi1 is equal to psi1 comma psi2, like the commutator of those. Well, the first one I said is this, and the second one is corresponding to this. And the reason why I say that this is the two-dimensional analog of the strong residue theorem is that in their paper, it's like a 5-page paper, the way it's formulated is instead of like saying, okay, you have a two-form on some surface, projective, then you can take the sum of all points in a divisor and then sum over all divisors, that residue will be 0. And in this case, well, the only divisors are the vertical line, horizontal line, and the diagonal. So if you sum over all the divisors, that's like taking this z2 equals 0, z1 equals 0, or z1 equals 6. So that's it. And by the way, this paper, Partian, is the only paper that Beilinson-Drinfeld reference in their group. In step 2, okay, so yeah, I mean, when you say so, as a result, we get, I just erased what we wanted to show. So we get a map from, let me get the dual correct. So we have a map from omega n to u g k. Step 2 is to define a map in the reverse direction. We define an inverse map. Psi k. And the inverse map, let me first, there's a very long, scary formula. Let me first explain what it looks like in the case of the most easy case. So when the algebra is trivial, one-dimensional, and when n equals 1. So I don't think you can get much simpler than this. So the map is, now in this case, so I want to map from star to omega. So what I will do is take a functional on the formal power series, and I need to give now a form. The form will be defined this way. I ranges over all integers, so it's infinite in both directions. Now, why is this an inverse? Well, let's just see what happens to the composite. Forget which side it's inverse I want. This way. Okay, so I take a lambda, map it to this omega, and then I map it to some lambda twiddle defined by the pairing, the residue pairing. And the residue pairing, well, what it does is it takes z to the I. So it's lambda twiddle defined using psi prime. It maps to the residue of z to the I times omega. But what is z to the I omega? Z to the I omega, well, the -1 term is lambda z to the I. So if I take the residue as equals 0, I pick up lambda z to the I. Okay, so I showed lambda twiddle equals lambda for all z to the I. So this is equal to 1. So this is the map, the inverse map in the most basic example. In general, you can see sort of how it must be built out. You need to take into account both the Lie algebra structure and the multivariable structure. So it's just this formula in general.
So sorry, I just want to ask about this formula. I'm confused because isn't it supposed to take values in some kind of Laurent series thing? So how does the fact that it has any negative terms on it cause a problem? Yeah, just not comprehending the definition, but
Yeah, I mean, really to make sense of this dual, I need to like form like this direct limit system where I bound the negative degree by n, and then took the limit over all n. Yeah, so I'm.
oh, I see. So it'll be the lambda of CPI will be 0 for I sufficiently positive.
Yeah.
That's the point. Yeah, I see. Okay.
Yeah.
So it is one.
Yeah, but sort of if you want to work, you can also work completely formally, and this will be like just using these will be so-called fields, like if you allow infinite direction in both directions, and you can like do manipulations just formally with fields without worrying about convergence issues.
But what you can't do is multiply them, right? So some.
Well, you can multiply a finite expression by infinite in both directions.
Right.
So this is fine.
Right.
But you cannot multiply two fields together.
Right.
That's yeah, good. Thank you. So in general, yeah, how do we define it? So prime, you take a function and we map it to, well, first we need to understand. So given a function, I need to give you with n plus 1 to 4 forms. The rth term, where r goes from 0 to n, will be defined this way. So first I arrange over all r tuples of integers, and then I arrange over all basis elements of G. So this bracket, I mean like the steps 1, 2 of the dim G. Okay, and the expression is that is impossible for me to do this. Okay, so here e I to the L will be e I times z to the L equal a basis of k. So e I is the basis of G, and z to the L, where L is the integer, is the basis of k. So please denote the basis of gk, the PBW basis. And then the superscript will be the dual basis. And I think that's, yeah, that's all. And now I can at least convince you that this is the inverse pretty easily. So lambda, I mean, to show like the uniqueness of lambda, I just test it on these basis elements. So if I hit lambda by this basis element, but instead of subscript, I put superscript, sort of ei1, comma e more I1, like those will all just out, I get 0. And then I hit z1 to the L1, zr to the LR. So then this becomes just like z1 minus 1, zr minus 1. And then taking residue, residue. So that kills everything here, and you pick up exactly this coefficient. So I'll summarize that over here. So it's clear that type K is inverse type K prime. It's also clear that it is injective. Well, the only way you can get 0 on the right hand side is if each of these coefficients is 0, but that just forces lambda itself to be 0. But as I've written it down, it actually does not land inside the space I want. Where omega r lands is actually inside here. So omega r sits inside star tensor r. See this one. So to show that so the only thing that remains is to show is that it satisfies like all the conditions I want, which I'll spell explicitly. That we want to show first that omega r is symmetric. Then we want to show it has the correct poles. And here, we want it to be simple. And finally, we want the omega r's to satisfy the residue property. Okay, so let me always 1, 2, and 3. So I claim all 3 of these properties are immediate from something very general, a general property of vertex algebras. And I'll just explain what we use. So properties 1 and 2 follow from the locality property of vertex algebras, which you don't need to know what it means, but just I'll say as what it implies is that we can define this omega r twiddle as multiplying omega r by the square of the Vandermonde. And the property is that this new form satisfies the pole and SR equivariance property. Sort of checking items 1 and 2 for omega r twiddle are very easy. And then from that, you introduce the property of poles for omega r. And then for property 3, this is again something very classical. It's called the operator product expansion. Formula. And what this allows you to do, at least again in the very trivial case where the Lie algebra is trivial and like n equals 1, it says if you take 2 Laurent polynomials in W and Z and multiply them, then you can expand it as a Laurent polynomial in W minus Z with Z coefficients. So maybe should I write it down? Yeah, so I'll say this, which yeah, maybe I'll just write down directly how I'm using it, which says following. So introduce. I'm trying to define the minimum necessary to see how Lie bracket shows up. So introduce so-called fields. So for each basis element of the Lie algebra G, we introduce this field A sub I, which I mean, the motivation for introducing is like it's like a delta function for E sub I, and it's infinite in both directions. And then what the OPE says is that you can multiply these fields and sort of you expand it in the zeta minus nu direction. And then in the and then with coefficients in zeta. And then there are some additional scalars. Regular, and this really holds a moment down. So where
Theta minus u to the power of something. I think first. Like with in the denominator, do you want to take a power?
no, just the
Oh,
just one power, yes. So yeah, it's just one power, and then here it's only regular powers, like there's no smaller inverse. And I was going to write this down, then I erased it, but I'll rewrite it. What this means is for and sort of the way you can make sense of this formula. So what I'm really doing is I'm taking the power series 1 over s minus t and writing it as summation of s to the I, t to the minus I minus 1, where I is an integer. But I can also, so this is infinite in both directions. But then if I only expand it as a function s over t with some s to the I coefficient, then I is only like positive. Or I can do like t over s times s to the I, then I is only negative. So it's that what I'm doing is like I'm taking something defined in both directions, but only really looking at it what happens in one extreme. And then here the F, I, the Q are the structure coefficients. Oh. Like the commutator, they are the coefficients which appear when you take the commutator of the two basis elements that you get. And so there's the proof ones here. Basically, there's a commutator expression appearing here. And that is what explains the appearance of like in omega sub n. That's what explains the residue condition. It's like the fact that there's a commutator thing there is exactly because of the operator product expansion here. Yeah, there's like a lot to be said here. Like in Beilinson-Drinfeld's book on chiral algebras, they upgrade this to basically they make everything sheafy. Like you can encode OPE as like a constraint on sheaves. But yes, the proof ends here. I do want to make one final remark is all of these spaces are actually commutative algebras. Like as I define them, they're only vector spaces, but they're actually commutative algebra, where the product is given by the shuffle product. So just like with the symmetric algebra, if you view it as like the direct sum of the SI invariance of the I tensor power, if you multiply an I tensor and J tensor, it's not going to be SI plus J invariant. You need to sum over the cosets. That is what is called the shuffle product. You do the same thing here. That's how you get an algebra structure. And this universal picture I explained here, there's like 6 terms. Those are actually isomorphisms of algebras. Like the multiplication structure on jets induces multiplication structure, like a co-multiplication structure. And then the multiplication structure on the forms induces likewise on the dual. And then like those isomorphisms are all compatible with that algebra structure. So like, these really have a nice structure. It's like an evidence out here.
Any questions for the speaker?
For the mass spin algebra, like, I mean, if you wanted to check it, then you just use that formula, just plug it.
Basically, you just need to use this formula. Yeah, like this formula is the only thing is needed to show. It respects the algebra structure. And it's nice because you have like very explicit maps in both directions. One is you have this, the other one is you have a residue. Yeah.
Anybody else? Two, no. Okay, if there's no more questions, thank the speaker again. Right.